In this week's video, we will be discussing acids and base titrations. We will be doing two problems. The first problem says calculate the volume of 0.300 molar HClO4 needed to neutralize 4.22 grams of barium hydroxide. So the first thing that we need to do with all acids and base titrations is write a balanced chemical equation. The first thing that we will do is write our acid, which is going to be our HClO4 or perchloric acid. Then we are going to mix it with our base, which in this case is going to be barium hydroxide, BaOH2. Now it's important to remember for all acid-base neutralizations, one of the products that we will get is water. The other is going to be a salt from the ions from our acids and bases. So we have our water coming from our H and OH, but now what do we do with the barium and the perchlorate? You're actually going to get BaClO4, 2, barium perchlorate. The issue now is that our equation is not balanced. We need two perchlorates. So we can put a 2 before our perchloric acid. Now we are going to need two waters. And so we have a successfully balanced chemical equation. The first thing that we want to do is start with our 4.22 grams of our barium hydroxide. This is the species that is acting as our base, and one that we can get to moles fairly easily. So we can take 4.22 grams of BaOH2 and go from grams to moles. This can be done using the molar mass of barium hydroxide. We can state that 1 mole of BaOH2 should be over the molar mass of 171.34 grams. We can cancel out our grams and grams, and now we have moles of barium hydroxide. So now how do we get to moles of our HClO4? This can be done using our balanced chemical equation. So in this case, we are wanting to say for our numerator that we are going to need 2 moles of our HClO4. This comes from our balanced chemical equation over 1 mole of our barium hydroxide. Make sure that you are using the coefficients from your equation. So now our moles of barium hydroxide will cancel and we're left with moles of HClO4. But now we have to look at our concentration to get a volume. Our last step is very critical. Our molarity is usually M equals our moles of solute, which in this case would be our HClO4, over our liters of solution. However, in this case, we want our liters of solution on the top and our moles on the bottom. So the way that we can do this is state that 1 liter of our HClO4 acidic solution should be over 0.300 moles of our HClO4. This is just using the reciprocal version of our molarity. Now we can cancel out our moles of HClO4 and we're left with liters of solution. If we put all of this into our calculator, you will get a value of 0.164 liters. But it is best for us to state that there are 1,000 milliliters in 1 liter. So we will receive a volume of 164 milliliters of our HClO4 acidic solution. In this problem, we had to go from grams to moles, then moles to moles using our balanced chemical equation, And finally, the definition of molarity to determine a volume. Then finally, what we ended up doing was converting to our milliliters. Our second problem for today states 20 mils of phosphoric acid, H3PO4, were neutralized by a 0.650 molar sodium hydroxide solution. If the original concentration of the H3PO4 was 0.475 molar, calculate the volume of sodium hydroxide used to titrate all the acid. The first thing that we should do is write our balanced chemical equation. This equation is going to differ from our last problem because we have a different acid as well as a different base. So we have our H3PO4 plus our sodium hydroxide. Just like the last problem, you will get water as one of your products, and you will get the sodium phosphate salt. So our sodium and our phosphate will mix. Sodium is 1 plus, while phosphate is 3 minus. So you will get Na3PO4. Now we must balance. Our phosphates are balanced, but our sodiums are not. So we can put a 3 in front of our sodium hydroxide. This now means that I need to have 3 waters to balance, and we have a successfully balanced chemical equation. So now I want to start with the molarity of my phosphoric acid. We can state using the definition of our molarity that 0.475 moles of H3PO4 is included in 1 liter of our acidic solution. This is using the definition of our molarity. Now what we need to do is multiply by our volume. In this case, it would be 20 milliliters. But now because we have milliliters versus liters, we should convert that 20 mils into liters. This is done by multiplying by 0.020 liters. So we'll cancel out our liters, and we can get a moles of our H3PO4. That value is 0.00950 moles of phosphoric acid. Now we need to go to our base. This can be done using the balanced chemical equation and our stoichiometric coefficients. So because we want to go to our sodium hydroxide, we get 3 moles of our sodium hydroxide for every 1 H3PO4. This is using our coefficients from our previously balanced chemical equation. So now our moles of phosphoric acid will cancel for both, and we can get an amount of moles of our sodium hydroxide. If we put this into the calculator, you should get 0.0285 moles of sodium hydroxide. So now that we have our moles, we need to use our concentration, very similar to what we did in problem 1, to determine our volume. So we know the molarity, so we can state that 1 liter of sodium hydroxide can be put over 0.650 moles of our sodium hydroxide. Our moles and moles will cancel, and we'll be left with a volume in liters. That answer is 0.0438 liters of our base. But if we multiply it by 1,000, we can get a much easier volume of 43.8 milliliters. In these two problems, you can see how it is important to use the balanced chemical equation for our different acids and base titrations, as well as using basic stoichiometric principles and the definition for concentration in order to solve our acid and base titrations. Good luck.